The question mark really has semantic content. So it was a deliberate choice. I'm really grateful for the time that I've had in London so far, and I'm already anticipating missing London when I will have to move on to the next stop of my sabbatical in January. I want to ask a question of you all at the very beginning. The question that I want to ask you is, why is my clicker not working? All right, the real question
is in crisis. That's fine.
The real question is, what are these politicians doing?
Power pose, yes.
Ah, very good. Power posing. That's exactly right. These British politicians are power posing. So for those of you who are not aware of power posing, you can see them demonstrated. I'm going to embarrass myself right now because I'm going to power pose for you also. So to power pose, you need to widen your stance. This is a little bit extreme, but you widen your stance and you put your hands on your hips like this, and you project the image of your favorite American superhero, right? Like, could be Superman, it could be Captain Marvel, whatever. You're gonna, your chin up, shoulders straight, align your back, project like this, right? Okay, when you power pose, the idea is not only do you project power inwards, but you also project power outwards. The reason why these politicians ostensibly are power posing has to do with real academic research on the effects of power posing. This is an extremely influential article by Carney, Cuddy, and Yap from 2010 in Psychological Science. There's this question, can power posing, these postures actually cause power? This empirical research concludes that it does, right? Posing and displays of power caused advantage and adaptive psychological, physiological, and behavioral changes that a person can, by simply assuming 2 simple 1-minute poses, not just embody power, that they can instantly become more powerful. And this has real world actionable implications, actions that these politicians were actioning. Now, if you're familiar with this, of course, the British press love this because everyone would read an article on these British politicians making fools of themselves. Yet, they were clearly given advice, policy relevant advice by their advisors, right, about what they can do to, and because they're politicians, obviously this is what they want, be more powerful. There's just a problem with it, and it's a problem that I think might have become obvious to you already. It doesn't work. Unfortunately, by doing this, I just become ridiculous, right? I don't actually exert any more power on you than I had before. Maybe like if I'm in the mood, I can have a psychological change, right? An inward psychological change. And that could have some real differences in my behavior. Subsequent work on power posing found that after amalgamating lots and lots of evidence about the effects of power posing, the only effect that seems robust under the circumstances that people are interested in is that inward psychological effect. But that inward psychological effect doesn't translate to the sorts of changes that reflect people's perceptions of you, right? The reason why this is a big deal is that this is just not a funny, isolated case. Around this time, lots and lots and lots of examples of this sort of phenomena where seemingly solid empirical research turns out on further collection of data to be ultimately groundless. Research that has been used for policy implications oftentimes in the human sciences, right, has somehow gone wrong. The original evidence for these effects were misleading. I'm going to be focusing on, well, maybe I should say that in addition that this sort of perception, right, of this problem has even been given the name of a crisis. So this is a survey done by the science journalist Monia Baker in the journal Nature in 2016. Baker surveyed Nature readers of various scientific affiliations, asking them many different sorts of questions. I just focused on one here, and I'm going to set aside methodological issues about survey sampling. This just gives us a qualitative idea that people are aware of this issue, right? And they have some concern for it. And let's not focus too much on the survey methodology issues, although we can talk about that if you want to. The important thing I want you to focus on is that 90% of the people surveyed thought that these sorts of episodes provided evidence that there's some sort of crisis to some degree or other in science. In particular, this is a very famous plot and there's a lot going on. I'm just going to focus on a few features to highlight for you. This is from a study done by the large-scale collaboration, Open Science Collaboration. You would think that it's counterintuitive, right? You would think, oh, like surely this is not a collaboration of a large number of people, but it is. What they did is they took roughly 100 different studies that had been published, mostly in social psychology, but some also in cognitive psychology, and tried to run the studies again that they found during this period of time. What this plot shows is it plots the original effect size that was found in those studies on the horizontal axis versus on the vertical axis, the effect size that was found in the new replicated version of the study. So what they found after they ran the study again. An effect size is a kind of normalized way of measuring how big a type of phenomena is in this science. We don't have to go into too much details. Just think of it as it's a normalized measure of understanding how big an effect is. Now, if everything were hunky-dory, is that a phrase that, okay, good, right? Then you would expect everything to kind of lie along this axis going diagonally across the page here, because that axis represents studies, right? Each point here, each bubble is a pair, right, of an original study and a replication study. You would expect, if everything were hunky-dory, for these bubbles to lie very closely clustered to the diagonal. That would represent a situation where the new study found a magnitude of an effect that was about the same as the magnitude of effect of the original one. But as you can see here, that's not what happened. There is some clustering along the diagonal, but there's this kind of like very heavy belly hanging off of the diagonal here. In this particular case, a lot of these are clustered either close to the horizontal line or to a line that's very close, a horizontal line that's just above that. These represent situations where the original effect size that's measured doesn't have very strong correlation at all with the effect size that was measured in the replication. In fact, that the size that was measured in the replication is very close to zero, almost an entirely negligible effect. The color of the dots correspond to whether or not the replicated study passes a certain type of statistical significance test. We're going to come back to significance testing later, but the main thing that I want you to focus on is the fact that things are not clustered along this diagonal axis. There's a lot that are clustered around an additional horizontal line here. And this is understood as really strong evidence that there's something going wrong in the methodology here. Seemingly solid studies that seemingly present solid evidence, right, for all sorts of effects, once they're replicated, right, once you run the study again, produce wildly different results. The crisis is a crisis of confidence in some sense for this methodology. This methodology that's undergirding social psychology and parts of cognitive psychology and perhaps other disciplines as well, has something deeply rotten in its heart. There's other sciences that have been implicated in this, and I haven't presented the evidence to you for that, but I'm just going to read them off to you, right? People have found similar things in certain parts of genetics, in cancer biology, in certain parts of neuroscience, especially preclinical medical science. And there's some evidence for this as well in experimental economics, although the evidence in these different places is of different degrees and different magnitudes. How do we explain what's going on here? What is involved in the source of this crisis? There's many things that people have implicated. Some involve low-powered studies. These are studies that have a low probability of finding the effects that they're looking for at the sizes that they're expecting. Other things that people have implicated are publication bias. This comes in many forms. One of the relevant ones for our discussion today is the fact that the criterion for how a study gets published doesn't just depend on whether or not the methodology was good. It also depends on whether the results are sufficiently exciting or interesting. That means that studies that are unusual and surprising selectively get published over ones that present evidence that a possible effect that you might have thought could be interesting that exists doesn't actually exist. Those sorts of things are less likely to get published. And so the evidence, the total evidence that we have in the literature is not a total reflection of the total evidence that was collected. Another has to do with questionable research practices. This name refers to a whole domain of different sorts of activities that in some disciplines are regarded as methodologically questionable. Here, questionable really is supposed to refer to a gray area where the distinction between whether something is allowed or not allowed is not really clear. There's clearly some circumstances where they're not good, some circumstances where they are okay. What's the boundary? You gotta kind of, use your internal organs to like suss out, make a judgment call. Things like, for instance, removing outliers from your data set. That's a common example. Another, which has sometimes been called research or degrees of freedom, involves the following sort of aspect. In a lot of these disciplines, when you go out to do your data analysis, you have a lot of choices in exactly particular ways that you can analyze your data. And it turns out that if you are allowed freely to make these sorts of choices, it can lead the final results of the data analysis to depend quite sensitively on those choices that you make. In such a way that if those choices that you make are not accounted for, it can produce a type of bias that's very similar to publication bias. Another factor, low incentives for doing the sort of replication work that we saw exhibited before. Within these communities, although things are changing now a bit, there's not very much scientific credit that a scientist could potentially get for doing one of these studies. Insofar as they have to survive in the fierce credit economy of academia, it seems like a bad investment of their time to be working in these sorts of studies. And there's another factor, which is high incentives for hype, right? If your work you can publicize, maybe extend its implications a bit further than are really tenable. I'm sure none of you have ever done that. You're more likely, right, to get more attention for your work, right? That's a way of spending a little bit of time to get work that has a higher return. Now, there's too much here to talk about in one hour and a half afternoon together. I'm going to be focusing on what I think is as a prior question that I think is important for us to understand and try to answer before we can understand the relevant importance of these sorts of factors in different disciplines, which is what reproducibility is supposed to be exactly, or maybe even more importantly than the what question, the why question. Why is this important, right? Now, the work that I've been doing on this has been a part of a group of philosophers, psychologists, statisticians, and other scientists at the University of Minnesota. We have this little internal project called the Many Faces of Reproducibility that's drawing to a conclusion during this academic year. And I got interested in this sort of subject by working with them on this project. You might check it out. Here's what I'm going to try to do in the remainder of the time that I have with you. the first thing that I want to do is explain on what my view is the why question. What are the functions of replication and reproducibility? Some people draw a distinction between those different terms to mean different things. I'm just going to conflate them and slide between them in this particular talk. One of the things that is a consequence of understanding what the function of replication is how to measure it. Once you understand what something does, then you have a better idea of how to measure whether or not particular activities are doing it or not. And one of the implications is that, therefore, once we understand the functions of replication, we can see that a lot of the ways that people have been measuring that in the literature are not very well suited to actually measuring it. I'm going to make a different suggestion for how we should measure that is not original to me, that is in the literature, but I think has some additional things that can be said in favor of it. And then I'm going to draw some conclusions about what this means for the significance of replication, replicability, and how we can use this as an input to understanding the sources of crisis. Okay, let's start with the functions of replication. I pulled some quotes from some random folk who have said things about this. So here's an example from the social sciences, from Rosenthal back in the 90s, already wrote that scientists of all disciplines have long been aware of the importance of replication to their enterprise. This is about like the full content of the discussion of why it's important, right? So, and this is the typical thing that you find in this sort of literature. Scientists begin oftentimes, and this is not a fault of theirs, right? Their readership are not necessarily looking for extended expositions of this, but it's usually a recognition that we all know this is important. Everybody thinks in all sciences this is important, right? You already get a hint here of the idea that the reason why it's important in my discipline, in this case, in the psychological and behavioral sciences, is because we're a real science, and this is something which is important in all sciences, right? So you just do your universal instantiation. It's important in all sciences, therefore it's important in this particular science. Okay. You see a similar thing here in the discussion from the open science collaboration themselves. They say reproducibility is a defining feature of science and core principle of scientific progress, right? This is saying that if you don't have this, you're not really doing science, right? And that if you want to say that what you're doing is making progress, being good science, right? You got to have this feature too, right? This is a necessary feature for all science to be good, to be science. Here's one from a philosopher commenting on this. If this principle that we demand reproducibility of scientific results were not satisfied, then laboratory science would be impossible, or at least we wouldn't be able to ascribe any objectivity to its results. Okay. So one of the things that is going on here is there seemed to be this idea that this is important for all sciences, and so therefore it's important for particular sciences, just as a matter of universal instantiation. But folks haven't really made this very precise yet. One of the folks who have is this group of psychologists, Zwaan, Etz, Lucas, and Donnellan, this very interesting article in Behavioral and Brain Sciences from a few years ago. They actually draw from the philosophy of science to try to make this idea more precise. Here's what they say. Many philosophers of science and methodologists have argued that the ability to repeat studies and obtain similar results is an essential component of science. Here's the key part. A finding is elevated from single observation to scientific evidence when the procedures that were used to obtain it can be reproduced and the finding itself can be replicated. So the idea is that this is a condition in order to progress from data to evidence, and therefore to make progress in a science. What they argue is that this way of understanding the role of replication and reproducibility follows from understanding in psychology in particular, because that's what they're focused on, as consisting of Lakatoshian research programs. Let's look at a little bit more idea of this. Let's recall just very briefly that there's an aspect of Lakatoshi's picture of science at the kind of meso level. So not at the level of lots of different sciences, but at the level of some particular scientific research program. It consists of a collection of essential components. These are the hardcore of the research program. They're the defining conditions. If you remove one of the elements of the hardcore, you have a different scientific research program. But usually the hardcore itself doesn't make direct empirical contact with data. It usually says some theoretical things about some stuff of interest, but you need to add extra postulates that describe how the theoretical stuff connects with empirical stuff, empirical data. Elements of these are usually part of the protective belt. These are aspects that are, or ideas or concepts or theses or postulates that are added to the hardcore. They're not considered essential to the research program, but they help the research program make contact with empirical data. So here's the idea of progression versus degeneration. These graphics are taken from a very nice article by Hafstad and Smith. I recommend checking it out just for the data visualizations. It's really beautiful. They're focusing on a case about explanations of the ancestry of birds. And they're contrasting a hypothesis that birds are dinosaurs. Very simple hypothesis, but it turns out very well supported, with a different one that is more complicated. And because I don't understand paleobiology, I'm not going to try to say what it is. But the main difference between the two has to do with how this situation changes over time. What happens is you start with a hardcore, and you have some additional postulates that you use that are speculative, that connect the hardcore with empirical data. These start to accumulate, but some of them will get corroborated. You'll get some evidence for them. They then form a protective belt around the hardcore, in the sense that if you get further evidence that seems like it's in conflict with the whole program, you have reason to modify the protective belt rather than the hardcore. The idea is to preserve the research program and modify only the auxiliary additions. And you see in this particular case that over time, the protective belt gets more robust and gets more layers on it. These different layers provide, and you can literally think in terms of like strapping on like a really robust belt. Like the more of these that you strap on, the less likely that you're going to hurt something when you attempt to pick up something heavy. So the heavy pickup is applying to, okay, this is a bit of a weird metaphor, but the heavy pickup is like getting more data and confronting it with your theory to see if you have a conflict. If you do have a conflict, the protective belt will absorb some of the blow. The extent to which you do that, you have a progressive research program. But the extent to which you don't, in which you don't accumulate elements in your protective belt, and you always have to be introducing new postulates in order to try to accommodate the data without any sort of accumulation. This is, to the extent this is happening, one has a degenerating research program. Now, as you know, Lakatos used these ideas as a way of distinguishing between a kind of good science and a kind of bad science. I bet you can guess which is which. Now, what Zvan et al. Are trying to do is they're trying to adapt this idea to replication. How are they proposing to do this? This is what they say. Replications, in particular, a particular type called direct replications, which is basically just doing the same sort of experiment again, are an instrument for distinguishing progressive from degenerating research programs. The ones that have replications are the ones that are like this, the progressive ones. The ones that don't are like the degenerating ones. And hence, they say to distinguish in the long term scientific inquiry from non-scientific inquiry. So you see this connection with this perspective where we have a general theory about the nature and structure of scientific methodology. We have very general conclusions about that. Then we specialize in particular cases like psychology or experimental economics. Okay, there's some problems. Maybe you can think of a few. One of the things that you might think of is that the sort of activity that they're demanding is just not always possible in all sciences. So it can't be a feature of science in general. Think of some cases of certain sort of work in empirical macroeconomics, in astrophysics, in a large part of environmental science, don't involve redoing the same experiment. In fact, a lot of these don't involve experiments at all. And there's lots of sciences that don't directly involve experimentation or in which experimentation is not a central part of their methodology. Now, certainly we don't want to exclude these sorts of sciences, surely, right, from the pantheon of science. I like my theories of stars, right? I want to keep those. Those are real science. Another is an old criticism due to Paul Feyerabend. Feyerabend famously criticized Lakatosh's program or his theory involving scientific research programs on the grounds that it's actually normatively toothless on the degeneracy criteria, because it doesn't give you a criterion for how long something has to be doing ad hoc saves, how long it's going to take, right, in order for it to add anything to its protective belt before it's considered a failed research program. Right? And of course, Feyerabend famously said, if you don't have any criteria, you're effectively saying and agreeing with me, Paul Feyerabend, that anything goes, right? Right, Emre? Okay. I'm trying to, I can't really get the Feyerabend, but that's the closest I can get. But there's another one which has been recognized since the 1970s, although it's not often focused on, is that the general methodology here doesn't really handle statistical hypotheses very well. The reason why it doesn't do this is that the general procedure, remember, is by confronting theories with auxiliaries and protective belts with data, the method by which we progress from one of these circles to another is by finding data that's in contradiction with the conjunction of the hardcore and the protective belt. It's very hard to get contradictions when all of your theories give are probabilistic predictions or probability distributions. There's more to say about this, but it's a problem that is left unresolved by Zwahn et al.'s proposal for how we should understand why replication is important. I want to suggest something a bit different. To do that, let me contrast this top-down perspective where we begin with general principles about science, like about scientific objectivity. I have to do the echo to like make it really grand, right? And you start from these big ideas about science in general, and then you explain the importance as a global necessity, the importance of replication as a global necessity for all science, and therefore it has to be important or a necessity for particular sciences. This requires the same universal import for reproducibility and replication across all sciences. I want to suggest that when replication is important, it's important for rather bottom-up reasons. Here's my suggestion. We should instead begin with common types of research problems, especially underdetermination problems. The sorts of underdetermination problems I have in mind are not between grand theories, but between usually pedestrian theories and hypotheses that would explain the data that are really, really uninteresting. I'll give you more examples in a bit, but I mean examples like either we found this effect or I made a mistake in the data analysis, right? That's a hypothesis that would explain the results. It's really uninteresting. I promise you it's not interesting. On this sort of view, the goal of replication reproducibility, its function is to try to provide evidence to undercut this underdetermination. If we can find evidence against these alternative uninteresting hypotheses, we can shore up and make more robust the hypotheses that are of interest. So this explains the importance of this as a local, viable strategy for solving these problems. When the particular science employs them will depend on the particular local problems that science faces. So this is compatible with situations that sciences face problems where these sorts of strategies are not applicable. So instead of having a top-down, we have a kind of bottom-up. Now this is compatible with a universal import for reproducibility, but it doesn't demand it at the same time. So I've already told you one example here, right? One of the things that the so-called functional account of replication is intending to do is to classify different types of replication by the functions that they serve. I've already told you about one. This is sometimes called methods reproducibility, right? That your results are not due to mistakes in your data analysis. But there's many others. Let me give you a few more examples. Another really uninteresting alternative hypothesis that could explain your data is that it's just due to a bad sampling, right? the sampling that you got is not representative of the population. How do you rule that out? Well, if you collect more data, you can get more evidence that it's not due to that. Or that the results you got depended on contextual factors. So for instance, if you're working in psychological science, you may be only testing a group of folk from, say, who are undergraduates at your university, but the conclusions you want to draw presumably are not about the undergraduates at your university, but about the nature of human cognition or behavior or so on, right? In that case, right, you might get data from a more representative collection of the population of interest to show that the results don't depend on contextual factors that your theory of the phenomena that you're testing says shouldn't matter. That they don't arise from fraud or questionable research practices. That they generalize according to theory or hypothesis tested to an even larger or different population. Or that they hold even when the hypothesis examined is operationalized or tested in quite different ways. This is not intended to be an exhaustive list, right? This is just supposed to be examples of some types of low-level, uninteresting hypotheses that we want to rule out. Which of these a science encounters are going to depend on the particular details of that science. But each of them involves a different type of replication or reproducibility that's important to it. There's a lot of things about a science that determine which of these will happen. These things involve the kinds of scientific problems that are addressed, the goals that scientists have for solving them, the types of experimental and data analytic techniques that are used, the nature, the complexity, and the diversity of the objects studied, the state of the development of the overriding theory. So for instance, in psychological science, there is very little overriding theory. One has rather lots of local mini theories that don't necessarily have implications for each other. That's a very different situation, for instance, than what we have in physics, where there is much, much more unified theory that is highly constraining for the possible hypotheses that people test. But also the cost and availability of evidence. One of the things that's interesting about psychological science is that evidence is widely distributed and is of a moderate cost, right? So what I mean by that is that every researcher in psychological science needs to reimburse their experimental subjects, their people, right? There's a moderate cost for that. And if you're at a university, there's some folks around. So there's some wide availability of evidence. But it's very decentralized. In comparison, you might think about high energy particle physics. In high energy particle physics, you've got the whole community has got like one instrument, right? So they have to agree and pool their resources together to decide what experiments they're going to run. Evidence is extremely costly and hard to get unless the community pools together. And these affect, right, the sorts of reproducibility and replication problems that they have to address. Another have to do with institutional features of the discipline. I've already talked about distribution of resources, but also differing structures of incentives in these different disciplines. In some disciplines, it's more acceptable to redo someone's experiment because you can get credit for it in your community. If that sort of difference is there, they face different sorts of problems than those for which there is low incentive for replication. This is also not intended to be an exhaustive list. This is supposed to be indicative of the sorts of considerations about the internal and external organization of scientific inquiry that determines or specifies how these local questions of underdetermination arise and need to be addressed. Okay, that's my story for what replication's function is. If you accept that story, what does it say about how we should measure replication, or in particular, how we shouldn't measure replication? Here is a very small, so small that you can't really see it, but at least it reminds you, right, of the plot that you saw before at the beginning, right? This is the OSC study. They measured rates of reproducibility using the data that they had. And depending on which measure that they used, they concluded that between 36 and 47% of their studies replicated, that the results in the new study were the same as the one in the old study. Here are some of the measures that they used. The replication team's subjective judgment. Significance level thresholds, whether they pass the same significance test or type of significance test at the same size. If you don't know about significance tests, don't worry. It's just a statistical test that has a yes or no result to it. A different type of statistical test, they tested whether or not there's a significant difference between the results of the two studies. If that difference is significant, that's this third measure. Another, does the old effect size fall within a confidence interval for the new one? A confidence interval, right, is a way of specifying not a yes or no answer, but a range of values of an effect size that's compatible with the data that you observed. So this asks, is the old effect size fall within that range, that new range? Now, one of the things that you see about all of these is that they're all binary measures. They're all yes or no answers, right? Either you replicate or you don't. That's wrong. And there's a lot of reasons why that's wrong. In some of my work, I provide a lot of different arguments for this. I'm just going to provide you one argument, which is the simplest. It's a syllogism. Okay, so we've already taken on board that the function of individual replication efforts is to confirm at least one of many auxiliary hypotheses, right? These auxiliaries are things like, I didn't make a mistake in the data analysis. My data is actually representative of, or sufficiently representative of the populations I'm studying, stuff like that. Here's another pretty uncontroversial. Confirmation comes in degrees. Okay, I get some nods. Excellent, you're on board. Therefore, the results of individual replication efforts, right, come in degrees. So binary measures or just don't reflect the fact that these measures of evidence come in degrees. They don't even fit the function of replication by formal criteria alone. Okay, if we don't use these binary measures of replication, what can we do? OSC do consider one other measure. In statistics, this is known as meta-analysis. It's a class of statistical techniques that involve combining or amalgamating evidence from multiple different scientific studies. The idea of meta-analysis is you take all your data, you pull it together, and then you say what your total data, your total evidence says about the subject or phenomenon of interest. Now that sounds like it's a pretty obvious thing to do. I think it's kind of obvious, why wouldn't you want to talk about all your evidence, the total evidence that you have, instead of doing some weird counting thing, right? It turns out this is a bit controversial, but I think that this is the right answer. This is the way that we should understand the import and how we measure the effects of replication by combining or pooling our evidence together. I want to say that replication is for meta-analysis in the sense that these different types of replication are functionally the input to these amalgamations of evidence, these meta-analytic studies. There are some psychologists who agree with me. This is a quote from Brewer, Thomas, and Rosenthal, same Rosenthal as before, actually. They have a particular version of this that they want to emphasize. They call it continuously accumulating meta-analysis. In CCMA, we combine the data from all the studies we've completed so far, and we compute various indexes to measure the degree of confidence that we have that a bona fide phenomena is being investigated. In other words, the individual effect sizes, right, of the entirety of completed studies are pooled into a single estimate. So we take what different portions of the data say about the phenomena, and we pool them together to say what they say about the phenomena together. This approach shifts the question from whether or not a single study provides evidential weight for a phenomenon to the question of how well all the studies, that is all of our evidence conducted so far, support conclusions with regards to the phenomena of interest. Okay, so this idea is not original to me, right? But it's one that I want to plump for, and ones that I think that my analysis of the functions of replication help us adjudicate, because this position is actually somewhat controversial in psychology about whether this is the right way to understand our total evidence. Let me give you an example for how this works. This is, and I really have more or less taken this at random to find a plot that is very easily understandable. So this is not taken to be an endorsement of the interest of this particular type of research question. Okay, what is the research question? Is a threat to one's moral purity, does it induce the need to cleanse oneself? Okay, so there's a lot of different ways to operationalize this. One particularly lurid way of doing it is you have people read gross stories, and then you give them the opportunity to buy soap. And if they're more likely to buy soap, okay, you see where this is going. There's other more interesting ways of operationalizing it. Now, a lot of the work on this has shown that it's hard to find really evidence that people actually do this. Here at the horizontal axis, we have the effect size. This is the same effect size that we saw before. And this vertical line is 0 effect size. So that is to say that threats to your moral purity make no difference to the need to cleanse yourself. Okay. So each of these studies, which appears in each of these rows, produces an estimate of the effect size and a confidence interval. The estimate of the effect size are these boxes, and the confidence intervals are the horizontal bars. So you see that lots of these are intersecting 0. A lot of these, the data is compatible with there not being any effect. However, when we combine all of the data together, we get an estimate that has an interval that is very, very small. So we find that when we do combine these, and this is on the assumption that we do want to combine these, this is on the assumption that the evidence provided by these studies is of a comparable quality, for instance, right? That we think that it's appropriate to weight them equally together. There are other techniques of meta-analysis that allow you to weight different types of evidence by their quality. I'm just using a really simple example because I didn't want to go into any technicalities here. So this is the most simple example of the sort of thing that you can do. And the result is that through lots of studies that show there's not very much evidence, that there is an evidence for a very, very small effect. This looks like an effect size of like about 0.1 or 0.15. Not much to write home about. And typical actually for many effects investigated in the social sciences and psychology in particular. But this is the general qualitative form of how this sort of work proceeds. Brian, how am I doing on time?
You're great, you got 10 minutes.
All right, we will continue then. I just wanted to emphasize here that meta-analysis allows us to address many of the functions for replication that I mentioned before. They allow us to address the question of whether or not our results are due to sampling error, because it allows us to combine together data to find evidence against this alternative uninteresting hypothesis. They allow us to check whether or not the results depend on contextual factors, because you can combine data that involve different contexts. They also allow us to test whether or not the results generalize to larger populations. How do you do that? Well, you combine data from larger populations. It's really that. It's not hard, right? So, and also the same thing when a hypothesis examined is operationalized or tested in different ways. You combine data from different operationalizations. That's it. There's some things you can't address with this. You can't address questions about fraud and questionable research practices. Insofar as one wants to address those, they have to be addressed by other means. Some of these work in concert with meta-analytic techniques, but not all of them do. And they don't test whether or not results are due to mistakes in data analysis. You have to do something else for those. But for most of the functions of replication, meta-analysis is the way to go. And in particular, it allows us to amalgamate our total evidence for and against these sorts of auxiliaries. This has some implications. So one is that it focuses our attention on the idea that replication is not a thing that we should be thinking about as a result, but rather as an activity or a process. It focuses our attention on the process of accumulating more evidence. And it pushes us to withhold facile judgment from single published studies, from small pieces of evidence. And it appreciates the weight of cumulative and multifaceted evidence when it's used correctly. Some technical features, I already mentioned that non-significant studies can add up to significance. Lots of small pieces of evidence that are not really conclusive at all by themselves when added up together can be conclusive. And also for people who are really geeks about statistical methodology, both classical and Bayesian methodologies are available for meta-analysis. There are some objections that you find in the literature to using meta-analysis. This is why I was saying this is controversial. And one has to do with bias. So I told you a little bit before about publication and bias. Reporting bias is very similar to that. We don't need to go into the distinctions. But the idea here is that if you combine a bunch of data from a collection of studies that are not representative of the total evidence, the result that you get from that combination, that meta-analysis, will also have the same sort of bias. That's true. However, I'm attracted by the tu quoque, right? Any replication measure has to deal with this problem, right? And even if you measure replication by binary criteria, you still face the same problem, right? That the total evidence that you've accumulated is going to be biased in the same sort of way. So it's not a special problem for meta-analysis. It's a problem for figuring out these sorts of issues, whatever sort of replication measure you use. But I also think that there's a little bit of a red herring to it. Okay, different sort of strategy. What the evidence says is different from the question of whether the evidence is misleading. What meta-analysis does, like any other procedure for amalgamating evidence, is it tells us what your total evidence says. And that's compatible with your total evidence being misleading because your evidence is collected using a biased methodology. One of the things that has been done is that the quantitative nature of meta-analysis permits tools to detect and correct for those biases, tools that are continually being developed. So even in the last 10 years, then there's been a lot of advances in different techniques and tools for detecting these sorts of biases in data sets and even correcting for them. I'm not going to go into the details of those, but I want to emphasize that by taking this quantitative route, we can actually better address the underlying problem that's being raised here. Another sort of objection that's often made is that there's many ways to do meta-analysis. There's many choices that you have to make. This is a little bit like the researcher degrees of freedom complaint that I mentioned before. And these lead to different results. That's true, and you can find cases where this has happened. However, at the same time, many of these cases are cases of transient scientific disagreement. There's historical evidence that these situations result from situations where the evidence is still inconclusive. And as more evidence is gathered, the community then forms a consensus over what the results say. The idea is that as more evidence is accumulated, the conclusions become robust over different choices of how to do the meta-analysis technically. So robustness analysis can help us determine what we can agree on and what we can't agree on. And that's totally compatible with the methodology being used here. All right, let me bring you all back to the main takeaways. Here's the first thing that I hope you'll remember. Replication's goal is confirmation and establishing reliability, especially through these various low-level, uninteresting auxiliary hypotheses. The second thing that I want you to remember is that because of that, binary criteria for replication are poor indicators for success at this goal. We should be using measures of success that are appropriate for measures of evidence. If we accept that, then we should be measuring replication through meta-analysis in the sense that it gives us the right quantitative framework for assessing the total evidence that we have for our scientific hypotheses of interest. If you found this presentation interesting, you can go and read the 3 papers that it's based on here on my website, or you can contact me and I'll be happy to send them to you. Thanks for your very kind attention, and I'm looking forward to your questions.